user or kernel code and data on some non-volatile storage. Non-volatile storage, which are going to be there even if the power is not there. So you might have seen in your shell programming, there are different types of devices, character devices and block devices. So hard disks and the secondary storage are block devices. So unit of data transfer is block. Block, I mean to say, is logical block. It's not, there has to be one more mapping between logical blocks and the actual data block, which is there on the hard disk. So a file may be stored across several blocks, or within a block, there may be several files depending upon the size of the file. Now, the important part here is file has several metadata items associated with that. Most important is name, extension, where it is located in the directory structure, and then finally, location on the disk. What is the type of the file? What are the permission, read, write, execute permission? When it is last modified? What is the size of a file? Which users or process have the file currently opened? So all these things are there in the metadata of a file. And users perform operations like creating, reading, writing, updating, deleting, renaming, truncating, and appending to a file. So when a file is created, a metadata is also created. And this metadata table or a metadata data structure records each and every operation, records each and every information. When you want to read or write from a file, read into or write from a file, it can be sequential, that you start from first block, second block, third block, and then again, if you want to start, you have to start from where you have left. Or it can be a random access. You can jump to a certain block number by specifying an offset. Now, how to play with the files, how to interact with the files? In most programming languages, you might have seen in your input output in C also, fopen, fread, fwrite provide library functions to implement all these operations. And actually, these library functions like fopen, fread, fwrite, all these are defined in stdio.h library, which eventually call the file related system calls provided by the operating system. Fine. So what is a file? File is a, you can say, a data structure or a record structure to permanently store the code or data. It may be a user data, user code, or a kernel code, user data or a kernel data. Every file is going to have a metadata associated with that. Various information about that file is going to be stored in that. Reading and writing can be sequential or random. And programming languages provide various abstraction or various library functions to deal with the files, which eventually call the system calls. Directories, or in Windows terminology, folders. Files are typically grouped into or organized into directories. And most operating systems treat directories as special files, where the content of the directory of this special file is just nothing but the list of files and their metadata. So when you create a directory using M, so you are actually creating a special file, and that file is going to have list of the files and their associated metadata. Now, how these directories are organized? So a directory can have another subdirectory, and that's how you get to see the path in Linux. The root, etc/fstab/this/this, and so on. And if you finally see the complete directory structure, you may get to see later on that it is just nothing but a graph. The whole arrangement of overall directory structure is nothing but a tree, which can be a graph also. And this graph can have, or this tree can have, one or more levels of depth, depending upon how many subdirectories are allowed, one inside another. Most OS permit up to maximum configurable depth of directories. Maximum limit on the number of files in a directory is also there. At a very basic level, graph of directories and subdirectories can be treated as a simple tree. And then we'll also see that how we can have cross links if it is supported by OS like Linux support, x86 support, that we'll see the cross links also, that from one directory, cross link can be there on a file to another directory. Fine. Like in Windows, you create shortcuts and desktop. So we'll see all those kind of things. Fine. Directory structure. So this is a single level directory. Fine. For all users. Now the problem here is it's a naming problem. Fine. And grouping problem also. We can have a two-level directory where every user would be having its own directory. And now, suppose user 3 is having a file test, and user 1 is also having a file test. So the file name of user 3 test is user3/test and / the file name. And file name of user 1 is user1/test and the file name. This can give you efficient searching. Can have same file name for different users. In single level directory, this problem was there, naming problem and grouping problem. This is how Linux look like. Tree structure directory. Later on, we'll see that actually it is a acyclic graph directory. Tree structure directory gives you efficient searching. We can have absolute name or relative name. So absolute name may be first / this file name. Relative to another directory would be /prt/first file name. You can discuss about current directory. You can use cd command, change directory, cd dot current directory, cd dot one level up directory. You can have absolute or relative path names. This is how somehow Linux look like. Now most important, inode. As I told you, every file or directory is going to, because directory is also a special purpose file. Every file or directory is going to have data or metadata and metadata. And this is going to be stored across disk and memory caches. If it's a big file, the data file can span several blocks on the disk. Metadata of a file is stored in data structure, a special data structure known as inode or information node. Every inode is going to have a unique number. If a file is unnamed, it can be uniquely identified by its inode number. When a file is not in active use, so its metadata along with the file is stored on the disk. So inode is important thing where every file and directory is going to have a metadata. One person can unmute and tell me whether the Linux is visible or not.
Yes, sir.
Okay. So if I do ls, I can see various directories here. And if I do ls minus I, so you can see different inode numbers associated with every directory. So it's my home directory. Home directory is having many directory. Now suppose I create a file, and now if I do ls, you can see mp is created. Mp is not a directory, it's a file. And if I do ls minus I mp, sorry, ls minus I mp, you can see the inode number of the mp file. So inode number is the most important thing. So whenever a file is created or opened, so inode number is a reference point, and this inode is again a spatial data structure which stores information about a file. Fine. Any questions at this point of time? Any questions from anybody? Okay. So let's move ahead. In core inode or file control block, when a file is actively being used, means some processes are working on that file. An in-memory copy of the metadata is maintained. So inode is like there in the hard disk when file is actively getting utilized. So a copy of that inode is maintained inside the main memory in a spatial data structure of kernel known as file control block or in-core inode. What it does, it stores a copy of files on disk inode along with some extra information you'll get to know later on. When the file is actively being read from or written to by any process, and then modern operating system maintains a inode cache in main memory to hold several in-memory inodes depending upon what files are getting actively utilized. So inode is a disk structure. In-memory inode or in core inode or file control block is a main memory structure. So when a file is getting utilized actively, the copy of in disk inode is maintained inside main memory known as file control block. Linkings. Now, what directory entry does? So I told you what is directory. You can see here. Directory is nothing but having a list of files and their metadata. So what directory entry is? Directory entry is nothing but a pointer to the its inode. Inode is what? Inode is a metadata. So what directory entry does? It links a file name to its inode, store mappings between file name and inode number for all files in the directory. Now these directory entries can be organized in disk block in several ways. We'll come to that depending upon the operating system implementation. Now there are some operating systems which provide an option of adding a link to one file inode from multiple directories, which can create cross links between various branches of directory tree. Now, if that is the case, multiple directory entries can exist for the same file in many directories. Now, this is important point, and that's why I said that this tree structure can actually get converted into a graph structure, because then you may be having cross links. Means this reorder directory can have link to the this file also, or backward also. Reorder directory can have link to this file also. Fine. In this way, it can convert into a graph structure. Now you need to understand by yourself, when you use CP command or when you use MV command, move command, what happens? You have to, this is a reading assignment for you, that when you use CP command, when you copy a file or when you move a file, what happens? That's what you need to see. Now, because I told you that now multiple directories can have links to a single same file, fine, we can have a structure like a cyclic graph. Why we want to have it as a cyclic graph? If this graph contains a cycle, what will happen? The path will never terminate. So to get to a path or a path name of any file, if there is a cycle in this graph, you'll keep on revolving around that cycle and you'll not be able to reach to that path. So this is the duty of the operating system, to keep this graph a cyclic, and how it does, that's another story altogether. So what kind of links are provided? Operating system provide two flavors of linking: hard link and soft link. Fine. And we need to spend some time here. We need to spend some time here. Hard linking is directory entry in new location is created to map a new file name with the existing inode number. Mind you, when you create a hard link, no new inode is created. It's just a link is created to a existing inode number. We'll see when we create a soft link, a new directory entry is created to only map a new file name to the old file name. And you need to look up the old file name to locate the inode number of the old file. Means here, I don't know, maybe a new inode is created. So let's move to our Linux box and let's see. So right now we have this MP file, and suppose I do echo Mayank and write it to MP. Fine. So if I cat MP, I'll get Mayank. So what I did, the MP file was created. I have written Mayank into that MP file. So let's create a hard link. Let's create a hard link. ln mp mp1. Let us see whether it is created or not. Okay. Let us ls here. Okay. So here you can see when I created a hard link, it is getting listed as mp1. Let me cat the mp1. Okay, it is also showing Mayank. Let me echo something into mp1. Echo this is hard MP1. Okay. Okay. Let's cat MP1. Oh ho. So Mayank is removed. This is hard is there. Let's cat MP. Okay, this is hard. Let us see the inode number. So you can see the inode numbers are same. So when you are trying to write into MP1, actually you are trying to write to the same, you are going through the same inode to that file. When you are trying to write to MP, actually the same inode is involved. So when you create a hard link, the inode number remains same. Just a link is created to that inode. And we'll later on see that inode actually points to the data block. So this is hard. Mayank is getting written into data block, not into inode block. Inode is a reference point. Inode actually points to the data block where the data is going to be written. So to write into a file, you need to search for the inode, and that inode will point to a data block where the item is going to be written. When I create a hard link, actually one more mapping from anywhere else is getting created to that inode. Any questions here from anybody? Yeah, Atharv, any question?
No, sir, not currently.
Bhavya Gaur, are you there? Jatin Garg, Jatin Agrawal, any questions? Mr. Anurag Pandey, any questions?
No, so far good.
Okay. So let's see. Let me remove MP. So ls, there is a file MP. MP was the original file. So let me remove MP. Let's see what happens. Fine. So ls, MP is not there. Let's cat MP1. Yeah. So still you can see. So actually this inode maintains the reference count of hard links. So actual file is itself a link. When you create a file, it is a hard link you are creating. And when somebody else creates a hard link, these are the extra hard links. So when you create a file inside a directory, actually you are creating a hard link. So what is a file? File is nothing but a link to that inode. So inside a directory, a mapping of file name and inode is there. And that particular mapping can be done from another directory to this inode. So even if you create a hard link or a original file, inode remains up till the reference count, the hard link count is not 0. Fine. Now you can remove MP. Now what it is saying? MP is already removed. We can remove MP1. So done. So what we have learned here, when we create a hard link, a link is created to that inode. Now even if you delete the original file, still file remains, because original file was nothing but another hard link which was first created. Until unless all the hard links are deleted and the link count reaches 0, that inode remains and you can refer to that inode. Now let us create one more file. So we have created another file, softmp ls. Softmp is created. Let me write something into it. Echo ls softmp is there. Let's see what is written in softmp. I'm a soft link. Now let me create a soft link to this. Let's ls this. So you can see here a soft mp1 is listed but a different color. In older Linux, you may see an arrow from soft mp to soft mp1. In older Linux ls listing, you may see soft mp arrow soft mp1 as a listing. But here you can see a different color is there. So a soft link is created. Let us cat the soft link. Yeah, I'm a soft link. Let us see the inode number, ls minus I. Okay. Now the inode numbers are different. You can see here 1835372 and here 1835353. It means what? When we created hard link, only a link is created to the existing inode. When we created a soft link, another inode is created, which is pointing to the file, which is pointing to the data blocks. Inode block is a different block. So when we created soft link, another inode is created, which is pointing to the same data block which older inode was pointing to. Which older inode was pointing to. ये बात ध्यान रखिएगा, when you create a soft link, another inode is created which actually points to the data block of the older inode where older inode was pointing to. And that's why we are able to see the same thing. Suppose I write something into soft link. And let's get the original file. You can see here. Because both inodes are pointing to the same data block where actually the data is getting written. Think over it. If I cat soft MP1, same data. Now let's do one more thing. RM, let's delete the original file. And let's do the ls. See here, the soft MP1 is in inconsistent state. Because now this link is dangling link. Because the data block it was pointing to is actually removed because the actual file is removed with its inode. Now if I want to cat soft MP1, no such file or directory. I can remove this soft MP1. Let's see whether it lets us remove or not. Yeah, it is removed. Any questions from anybody? Yeah, Ajay want to ask something. Yeah, Ajay.
Yeah, thank you. So I couldn't understand or make out the logic for the soft link was visible, but as we tried to ls, it gave us this error message. So maybe I could understand soft link is created to have a acyclic structure. Uh, that is
No,
what
no,
is.
no,
But,
no, no. Thing is,
okay.
actually, I'm not having today my whiteboard. Otherwise, that would have been easy. Anyway, let me explain. Let me try to explain this. When I say soft link, as you have seen here, so look. First of all, we need to understand when we create a file, actually we are creating a hard link. So inside a directory, when you are creating a file, you are just having a mapping of file name, and a inode. What is inode? Inode is a metadata structure of that file. That inode in turns point to the data block where the file's data is going to be written. This is first thing. Now you keep on creating hard links. All these hard links are just going to be pointers to the inode only. And when you create hard links, there would be no extra inode created. It is just like mapping. Few more mappings would be created to this inode. When we create soft links, another inode is created. It's a separate inode is created as we have seen here. You can see here, I'm highlighting this line. So both are having different inodes. Now what this soft link is doing, because you are having a soft link to the initial file, soft MP. So wherever that soft MP inode is pointing to, new inode will also point. So where the soft MP inode is pointing to, it is pointing to the data block of soft MP. And there the soft MP1 will also point. Now, if you remove this soft MP, when you remove this soft MP, the original file, that's what we have done, where can this soft MP1 point to? Because when you remove soft MP file, the inode is removed, and accordingly, the data block of that inode is also removed. So this particular pointer, the pointer which was coming from the inode of soft MP1, becomes dangling. Dangling means it is having no target. And that's why we are not able to see the content of that. It's a dangling pointer. Dangling which is not having any target. I think I have made myself clear. Any other doubts?
Yeah, I think that's perfectly clear. So I thought
Yeah.
the data blocks themselves are keeping a reference counter, which is not the case, which doesn't make sense also. Yeah.
Yeah. Any other question from anybody else?
Just one thing. So Softling, they kind of help in rendering a acyclic structure. Is that a correct statement to say?
Whenever you create a soft link, actually how this directory structure is maintained inside, basically they try to have a tree structure, fine. And when they have a soft link, they keep a soft link or hard link, whatever link, they keep a special care of those links, the cross links. There's a separate treatment for that. Fine.
Okay.
So the motto here is only to avoid cycles in that graph at the time of traversing, because what may happen at certain point of time they may need to correct the directory structure, and this particular accounting keeps on doing in operating system. The operating system keeps on doing this thing, and then they keep on removing these dangling pointers. Fine. So this is where we don't end up into, in as a user, we don't end up into these issues, but yeah, operating system may end up into a cycle. So at the time of creation of soft link they keep it, and that's why some of the soft links and some of the hard links are not allowed. You may just check it, that whether you can create a soft link from downwards to upwards, and up to which level you can create, which kind of permission is needed. So one more thing I want to mention here, because you have asked, you cannot create hard links across the file system. So hard links can only be created within a volume where the file system is there. Soft links can be created from across the file system also. Because for soft link gives you one important thing, as and when you delete the original file, soft links, even if they are making cycle, they are of no use, because they are not going to point to any actual file. Got the point?
Yeah, sure.
Yeah, Sonu wants to ask something. Sonu Sharma.
Yes, sir. Oh, if we delete, sir, software MP1 first, then what
Okay.
happens? Sir? Data
Okay.
will be deleted or not?
देख लेते हैं, करके देखे ना. अब तो
Yes,
सभी डिलीट कर दिया, एक बार कर लेते हैं. हाँ.
yeah, okay.
तो एक फाइल बनाते हैं, टच MP. फाइन. तुम क्या कह रहे हो, इसका सॉफ्ट लिंक बनाए? सो
हाँ सर, और
ln
soft link delete
और
करें
सॉफ्ट
उसको।
लिंक को डिलीट कर दें. ln -m MP MP1. ठीक है, बन गया MP1. ठीक है, एंड कुछ लिख दें, MP में लिख दें कुछ ना.
Yes.
कि MP1 में लिख दें, एक ही बात है, किसी में भी
एक
लिखो.
ही बात है, yes, sir, yes, sir.
ठीक है. तो कैट MP1 कर देते हैं. ठीक है.
Yes, sir.
अब व्हाट यू आर सेइंग, रिमूव MP1.
MP1, yes, sir.
कोई दिक्कत नहीं, हो गया रिमूव. इसको रिमूव करने में क्या दिक्कत है? वो तो उसका आई नोट गया, उसका पॉइंटर चला गया. बात समझ में
Sir,
आया? पॉइंट दिमाग में रखो पॉइंटर को।
yes,
एक
yes.
आई नोड से एक पॉइंटर उसके डेटा ब्लॉक में गया, ठीक है?
Okay. Okay, sir,
और
understand. Okay.
गॉट द पॉइंट? पॉइंटर का
Yes.
कौन सा? अब हम कैट करें एमपी को, मिल जाएगा हमको,
हाँ सर, हाँ मिल जाएगा, मिल जाएगा.
ठीक है? एनी अदर क्वेश्चन?
No sir, thanks.
Any question from anybody else? Now the assignment here is you need to see, suppose CP, MP to कहाँ पे करें कॉपी इसको? To fine. Okay. What I have done, I've copied MP to desktop also. So पहले यहाँ ls करते हैं. यहाँ पे है MP. So let's see ls minus I MP. I node have 183.5353. Let's move to desktop. यहाँ पे ls करें, MP है. ls minus I MP. सोनू कुछ दिखा?
Sir,
दूसरा फाइल बन गया, दूसरा आई नोट के साथ, ठीक है?
yes
जब
sir, right.
जब कॉपी किया तुमने, ठीक है?
Yes sir.
गॉट द पॉइंट?
Yes yes sir.
ओके. अब एक काम करते हैं, हम नई फाइल एक बनाते हैं, टच सोनू नाम से बना देते हैं, ठीक? ls. तो अब हम करते हैं मूव. ठीक है? अब डेस्कटॉप चलते हैं, ls, ठीक? अब यहां वाली फाइल को देखते हैं पहले. हाँ, ls माइनस आई सोनू 835372. ऊपर चलते हैं, यहाँ ls करते हैं. यहाँ से तो सोनू गायब हो गई, मूव हो गई ना.
Yes sir, वो तो move हो गई. हाँ.
अब आपको रिलेट करना है. व्हाट यू नीड टू डू कि व्हेन वी मूव, व्हेन वी कॉपी, व्हाट एक्चुअली वी आर डूइंग. ओके?
Yes sir.
And how it is related with hard link and soft link. Got the point? Okay. So let's move ahead. Cyclic graph directories. File deletion. When you create a file, file is only linked to its parent directory by default. Multiple directories can create directory entries to hard link to this file, as we have seen, and can reference it with different names. We have seen that. We can name hard links with different names. The inode of a file maintains this link count. When you want to delete or unlink a file from a directory, you are just deleting that link, amounts to deleting the directory entry that points to that inode. और जब तक सभी ये लिंक खत्म नहीं होगा, हार्ड लिंक, it's not always going to result in the file being scrubbed from the disk. Unless all the hard links are deleted from all the directories, the file would be there in the hard disk. When multiple hard links exist to a file inode from multiple directories, when you unlink a file from one of the directory, it is still accessible via other links. We have seen that. The file is going to be garbage collected only when it is unlinked from all its parents and its link count reaches to 0. Mind you, the link count does not account for soft links. A file can be deleted even if some soft link exists to it. And at that point of time, the soft links become invalid. That's what we have seen just now. File tables. This is important. Please wake up if you are sleeping. The operating system maintains system-wide and per process open file tables for every file in active use. So क्या एक system-wide file table is there and a per process file table is there. And these open file tables store pointers to the inode of the open files, in-memory inodes of the open file. When a file is opened, suppose it is getting opened first time, a new entry is going to be created in a global system-wide file table, which will point, that entry will point to the in-memory inode of that file. If file was already opened and in-memory inode already exists, so per process open file table just point to the system-wide global entry, which in turn point to that existing inode. जब पहली बार फाइल खुलेगा सिस्टम वाइड ग्लोबल फाइल टेबल में एंट्री होगा which will point to inode. If file is already opened by another process and a different process wants to open that file, so the per process file table just point to that system wide file table entry, which is actually in turn pointing to the inode. If no in-memory inode is found when you are creating a file, new free in-memory inode is allocated to the file from the inode cache. So what is there? The operating system maintain an inode cache where empty or vacant inodes are there. So if no existing in-memory inode is found, then a new inode would be allocated to this file. And then you go to the disk and populate the memory version from the disk version. Every open system call always creates a new global file entry. Always create a count in a new global file table entry, to be very specific. But it does not always allocate a new in-memory inode, because if it is already existing, you just create one more entry that, okay, this process also has opened this file, which are all going to be pointing to the existing in-memory inode. Fine. In-memory inode maintains reference count to indicate number of open file table entries pointing to it. कितना open file table entry उसको point कर रही है. This in-memory inode is kept in memory as long as this reference count is non-zero. And as all the processes from everywhere the file is closed and reference count reaches to 0, the in-memory inode would be reclaimed by the inode cache. Do not confuse with the reference count of in-memory inode with the link count of an inode in the directory tree. That's another thing. That is like how many directories are actually having hard link to that particular file. This reference count is how many processes, different processes have opened that file. That is a reference count, that how many processes are actually accessing that particular inode. Do not confuse these two reference counts. Per process file table, you'll issue an open system call from a process, and every process is going to have a its own file table. This per process open file table is nothing but a array of pointers where every pointer is going to point to a system-wide open file table. When any user opens a file, index of this array is returned, which is known as file descriptor or file handle. तो क्या है? Every process maintains an array of pointers. Every process maintains an open file table, per process open file table, which is nothing but an array of pointers. These pointers are actually pointing to the system-wide global file table. Index, when you create a file, when you open a file, index of this array is returned. And this index is nothing but the file descriptor or file handle. In all future correspondence or interaction, this file descriptor is going to be utilized. Fine. File descriptor is going to be utilized by process when process wants to refer to the file. Mind you, it's very important. File descriptor number is local to a process. It is an index into per process, not the system-wide file table. आप कोई नया फाइल डिस्क्रिप्टर अगर असाइन करना है, so most operating system शुरू से शुरू करते हैं जीरो से, जीरो इंडेक्स से. Look through the array linearly to find the first unused index. Most OS looks the array linearly to find the first unused index. फिर से per process file table. Fine. When a process opens a file, an entry is created in a per process file table. This entry is nothing but a pointer to the system-wide file table. And system-wide file table actually points to the in-memory inode. This is the whole path. When a user opens a file, an index of that particular array is allocated to that file, and that is written, that index is written, known as file descriptor or file handle. This file handle or file descriptor is going to be utilized in all future references. File descriptor is local to that process. It's an index of that per process open file table. And how these file descriptors are assigned, OS looks into that array from 0 to linearly, and as and when it gets an unused file descriptor or index, it assigns to that particular file. Fine. Now you have seen in your system programming a special file known as pipe, and later on in computer networks course, next semester, you will see the sockets also. When you use system call to open pipe, you have used pipe system call. They create similar entry in the per process open file table. Actually, but these entries do not point to the in-memory inodes. When you create a socket, the file table entry actually points to a special kernel data structure, socket data structure. When you create a pipe, the file table entry points to a pipe data structure, where are some which actually allocate some kernel memory for that pipe to act as a buffer. And if you have seen carefully in pipe system call, there are two file descriptors which are written: writing end and reading end. Remember? Anybody want to ask any question here? Can ask regarding pipe. When you have used pipe, let me see whether I can show you the pipe program on internet. Mhm. Is this code visible to everybody? One person can tell the code which I am highlighting. Okay. So now if you can see this code, what is happening? Let's go to a simple code first. So you are using pipe where you have declared PFDS as a array of 2. So when pipe returns, it returns 2 values, 2 file descriptor. So you can use write to write into one end, and you can use read to read from the another end. This buffer is the buffer which is getting created, and this is 5 is the number of character you can have. In the next example, if you see, we have done close 1, and in child we have done close 0. So when I do close 0, anybody can tell me what happens? When I do close 0, anybody can tell what happens? Yeah, Athar.
Sir, I assume that the read end of the pipe will close.
I think you people have done this program in your system programming. Must have done. Yes or no?
Sir, we generally use direct pointers. We do not use means. I have not done close 0 per se.
Okay. Now I'll tell you there are 3 operating system special purpose file descriptor for every process. This 0, 1, and 2. 0 file descriptor is for standard input. 1 file descriptor is for standard output. So when I am writing a command, here, so let me explain this problem to you and then you will be happy. So what I am trying to do, let me see this program first. It is trying to implement ls then pipe wc minus l, ls pipe wc minus l. This is trying to implement this. So we'll see ls, okay, ls pipe wc minus l. What is going to give? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 entries. So if I see ls here, so ls are having 10 entries, so it is going to be 10. So what is happening? The output of ls should go to output of ls. If I write ls, it goes to the standard output. Fine. And if I write wc minus l, it should take input from the, suppose I say ls and write output to 1, say test. So ls output went to test. And if I say wc minus l test, let's see. Fine. It gives the lines because test is again written. Fine. So wc minus l is expected to take input from keyboard. ls is expected to give output to the standard output. wc minus l is expected to take input from the standard input. The standard input file descriptor is 0. The standard output file descriptor is 1. Now what this program is doing, it is closing 1 means it is freeing the index 1 of that open file table. It is clearing the index 1 of that open file table. क्लोज कर दिया यानी कि स्टैंडर्ड इनपुट स्टैंडर्ड आउटपुट से वो क्लियर हो गया. Now next is the another system called known as dupe. So what it is doing, whatever file descriptor is getting written, close के just बाद dupe use किया. So what you are trying to do, you are trying to create a duplicate file descriptor for PFDS1. PFDS1 क्या है? जो पाइप सिस्टम कॉल ने फाइल डिस्क्रिप्टर एक एंड का रिटर्न किया है. तो क्लोज के बाद ड्यूप यूज करेंगे तो ओएस क्या करेगा? 0 से शुरू करेगा. 0, अच्छा 0 एंगेज है, 1, अच्छा 1 फ्री है तो 1 को असाइन कर देगा पाइप के एक एंड को. Similarly in child what we have done, we have closed 0. Means we have closed the file descriptor, we have freed the file descriptor on index 0 of that array, and then we have used dupe. तो पाइप का एक एंड को स्टैंडर्ड इन बना दिया. And then this particular program is actually giving the output as if I'm writing this command ls wc minus l. So whatever is the output of ls, instead of going to standard output, it is going to one end of pipe. Whatever is expected as a input from standard input to wc minus l is actually coming out of another end of pipe. This is how you can play with the file descriptors to get to do so many cute things. Atharv, got it?
Yes, sir.
Hmm?
Yes, sir, I understood, sir.
Mr. Anurag Pandey?
Good, sir. Good, sir.
Okay. So, duplicating file descriptor, that's what I was telling you. Second file descriptor, when a file descriptor is duplicated, another file descriptor is created to point to the same global file table entry. Global file table entry has a reference count to keep track of the number of file descriptor pointing to it. Garbage collected when this count goes to 0. Example, when a parent process executes the fork system call, आपको बताया था जब fork होता है तो सभी फाइल शेयर रहता है. Parent initializes the child descriptor to point to the same global file table entries using this mechanism of duplication, and allows both parent and child to access same set of files. So when a file descriptor is closed in one of the parent or child, other can still access via its own file descriptor because the global file entry is still valid. In some operating system provides dupe system call, the way we have seen. Take a file descriptor in a process as input, creates another file descriptor to point to the same open file table entry. And I have shown you that shells or your terminals or command line interpreter use this dupe system call for various file descriptor manipulations. Fine. So fork, close, and dupe. The combination of fork, close, and dupe can actually give you so many interesting manipulation to do. So here what is going to happen, when I write ls, a new process is created. Fine. Then using fork, then shell is waiting. Remember the fork thing? When I write ls and press enter, a new process would be created, a new shell will be created, the original shell will be waiting. In a new shell, the ls would be exec. Fine. And when ls new shell exits, we get the command prompt again. So ls, a new shell, in new shell ls is executed, old shell is waiting, new shell exits after executing ls and returns back to the old shell. This is what is happening. When I say ls pipe wc minus l, so a new shell is created which is having ls. ls forks another child. In one look, shell is a parent, shell का child जिसमें ls चलेगा, ls का child जिसमें wc minus l चलेगा. ls अपने और अपने child के बीच में एक पाइप लगाएगा. ls अपना स्टैंडर्ड आउटपुट बंद करेगा. फाइन. और wc minus l अपना स्टैंडर्ड इनपुट बंद करेगा. कैसे? क्लोज और ड्यूप. wc minus l भी क्लोज और ड्यूप, और बीच में पाइप आ जाएगा. ये पाइप लगाया. सो शेल का चाइल्ड ls, ls का चाइल्ड wc minus l, और इन दोनों चाइल्ड के बीच में पाइप यूजिंग क्लोज एंड ड्यूप. Any confusions to anybody now? Yeah, Atharv, any doubts?
No, sir, this is clear.
Sonu Sharma, any doubts?
No, sir.
Okay. Now, what is a file system? अभी तक फाइल्स और बाकी चीजों की बात कर रहे थे. As I told you, file system is nothing but logical manifestation of your hard disk or secondary storage. It is a way to organize files on secondary storage. As you know, secondary storage disks typically has several logical partitions. So I'm not talking about the platters, physical platters. I'm talking about the logical partition. Fine. And then another thing you keep on hearing, volume. Volume and partition are sometimes confusing, but the simple way to understand is logical volume means it can be having one partition or many partition on the disk. A volume can have a complete disk or collection of several disks also. Later on, we'll study the redundant array of independent disk, RAID and all. We'll be coming to that. So logical partition, logical volume. A logical volume can have many partition or a single partition. A logical volume can have a complete disk or a several disk also. Every file system on a volume has a super block or master file table. कहीं कहीं इसको MBR भी बोलते हैं, master boot record. Now this super block actually stores the master plan that for how the entire volume is organized. मतलब यही बताता है आपको that which are the blocks which are data block, which are the blocks which are inode blocks or metadata blocks, which are the blocks which are free, and so on. So every FS, every file system on a volume is going to have a super block or a master file table, which is having the complete detail of whole volume. कहाँ कहाँ पे डेटा ब्लॉक हैं, कहाँ कहाँ पे inode ब्लॉक हैं, कहाँ कहाँ पे फ्री ब्लॉक हैं, so on. A file system on a volume can store 0 or more operating system or other user file. You can have 0 or more operating system in a volume depending upon your usage. If a logical volume is having an OS, it is going to have a boot block also, which actually contains the bootloader, and that bootloader pointer is there in the BIOS when you boot your system. Now we have utilized multi-bootloaders also, like GRUBs, Grand Unified Bootloader by GNU, where this boot block is actually going to have a grub loader, and then grub loader can let you choose which operating system you want to boot. So one more indirection in between. अभी native Linux है. If there is a native machine which is having a native Linux, only one operating system, so there would be having one boot block. That boot block is going to have a bootloader, and that bootloader information is there in the BIOS. So when you boot the system, BIOS actually goes to the bootloader, goes to the boot block. Boot block gives the bootloader, and then bootloader loads the operating system. When there are multiple operating system and you have a dual boot or triple boot system, then what is there? In our time, we used to have a Lilo, Linux loaders, different kind of bootloader. But nowadays we have grub. So you can have grub installed on a machine. So your BIOS will go to the grub. Grub will let you choose which operating system to boot. You can read by yourself. And at the same time, another reading assignment, that what happens when a system like mine is running. I'm running on Windows but using this VM. I'm running on Windows, but I am having my VM also here. Oh, caps the bike, yeah. Fine. So what happens when you have this kind of system that a VM is there? So I can give you a certain idea that, okay, when it boots, one operating system boots, Windows boots. Now Windows is having another thing known as hypervisor. In hypervisor, there has to be some indirection to the boot block of Linux so that Linux can boot within Windows and so on and so forth. So this particular thing, grub and VM loading, you have to read by yourself. Boot block is typically at block number 0, first block, and it is followed by the super block at block number 1. Now, another thing is, before a file system can be used to store and retrieve data, it must be mounted. Now, when you insert a pen drive, let me do this thing for you. When you insert a pen drive or any other drive, that nowadays you don't get an idea. But in our time, we used to mount that pen drive also so that we can access the data on the pen drive. So mounting file system is equivalent to opening a file before reading or writing into it. So there would be a native file system present on, there's a direct file system is what? Is a directory structure. So there is always a directory structure there. Now you want to attach one more file system, then you need to see for the mount point. And then using mount command or mount system call, you will be attaching a coming file system into the existing directory structure somewhere. So before you can actually utilize the file system, that file system need to be attached to the existing file system. Before any file system can be utilized, it has to be mounted to the existing directory structure. That is known as mounting. OS maintains an in-memory mount table which lists all the file system currently mounted. First file system that holds the kernel executable is mounted during the boot time at the root of the directory. Fine. And kernel executable can be read off the root file system during the boot process by the bootloader. तो जब सिस्टम बूट करते हैं तो रूट डायरेक्टरी पे फर्स्ट फाइल सिस्टम माउंट हो जाता है, ठीक है, जो नेटिव फाइल सिस्टम होता है. Now, if you want to read another file system, then you need to mount this file system onto the existing file system into some mount point. So let me see whether I can access that or not. Let me see. Okay. I'm not able to access the root file system. Otherwise, I would have shown you. But we can see this. I think DF may run. Fine. So these are the different file systems you have. Fine. These are the different file systems you have, which are actually mounted on udev is mounted on /dev, tempfs is mounted on /run, device sda5 is mounted on root. Fine. And so on and so forth. Fine. So, and you can see so this is a mount command to mount a file system. Fine. So you have to declare a directory and then mount -t type device directory. Yeah, this is standard form of mounting anything. Nowadays, your Linux is kind of intelligent. So as and when you attach a file system or a pen drive or CD drive or whatever, it mounts it automatically. But you can do it manually also by mounting a file system. Fine. We will stop here. We'll stop here. And if there are any questions, you can ask. Athar which wants to ask anything. Yeah, Athar.
Sir, when we mount a file system in an OS, is it similar to when we are sharing from Windows to the virtual box, or is it different?
Yeah, it's a that's why I wanted to show you the fstab file. So if you go and see /etc/fstab, like like VM is a different story altogether. VM, you are running VM as a process of Windows only. Are you getting my point or not? Fine. So when a VM runs, actually hypervisor runs, and hypervisor is a process which is running as a Windows process, and then VM runs inside that. The question you want to ask is actually related to something else. Suppose you have a dual boot system. Are you listening, Athar?
Yes, sir.
So you have a dual boot system and you are currently booted the Linux. But now you want to see the files of Windows also, which are there in the hard disk.
Okay.
How can you
so
do
in
that?
that case, I need to mount.
In that case, you need to first of all run df and see where is that Windows there. Then you go to that particular directory and can mount the things from Windows to Linux. So Windows file system can be mounted on Linux. If you want to do it permanently, because otherwise you have to run this mount command all the time, you need to run this so you can see here what file system mount point type options dump. So here you can see this etcfstab file gives you the option to, like here you can see the swap space is there. Fine. This etcfstab file, here you can write the mount points. That okay, which this so at the boot time this etcfstab will be run, and those particular mount file system would be mounted on your original file system. Fine.
Yes, sir.
Got the point?
Yes, I understood.
Any other question?
Sir,
Hmm.
I actually have another question.
Hmm.
When we say that hard link cannot be done across file system, what does across file system mean?
दो फाइल सिस्टम अलग अलग हैं. लिनक्स में ही कई फाइल सिस्टम हो सकते हैं. Like I've shown you, if you see the df, fine. If I run df, you can see device slash loop. These are all different files. Device SDF5 different file system. Loop 2, loop 3, loop 4. You have SDF1 is a different file system. So these both may be ext2, same file system. Type क्या है file system का, that is not important. But they are getting treated at different file system because they are having different boot blocks. Got the point?
Yes, sir.
Okay. So when
Yes.
you are saying different file system means they are different, treated as a different file systems. They are not in one volume. Fine. So
Yes,
these
sir.
are the different volumes.
Yes, sir.
And then the hard link cannot be created across the file systems. Any other question from the guests?
No, we are fine. Thanks.
Okay. Okay, I think if there are no questions, then we can end the meeting. Thanks a lot.